Okay, so in this video we're going to talk about how to solve problems involving inclined planes. An inclined plane is basically a fancy physics teacher way of saying a wedge or a hill. Okay, so we'll basically be doing problems with objects moving along a ramp, essentially. And these are really popular among physics teachers for some reason. Now, the only thing that makes inclined plane problems any different than the ones we've done before is because we have to use a different coordinate system that we're used to. But essentially, they're still your basic second law problem. You still follow the same basic process to approach these problems. It's just the coordinate system is slightly different. Okay, so let's take a look at the generalized inclined plane. Okay, so your basic inclined plane looks something like this. You have the plane itself, which is, just a ramp. Okay, you can imagine it like a ramp or a hill, whatever helps you. You have some object, like a box, that's on the inclined plane, and then there's some angle that the plane makes with the horizontal, with the ground, and that angle is theta. Okay, now in this case, it's drawn with the plane going up as you go to the right. You can flip this around, and it doesn't really matter. It doesn't change anything. I don't really care how you draw your inclined plane. If you draw it going to the left or right, it doesn't make a difference. Okay. But keeping this picture in mind, I want you to think about something before we get into problem solving. Now, if you have an object on an inclined plane, let me back up for a second. If we drop an object in free fall, we know that that object is going to fall down with a constant acceleration due to gravity. We've talked about that before. It's about 9.81 meters per second squared, or about 10 meters per second squared down. Okay, so let's say you have something on an inclined plane, and let's say there's no friction. Okay, so the only thing pulling it down the plane is gravity. Okay, what I want you to think about is this. I want you to make a prediction. If you place an object on a frictionless inclined plane, and the only thing pulling it down the plane is gravity, it's going to have an acceleration. Is the magnitude of that acceleration less than g, equal to g, or greater than g? Okay, so I want you to think about that. An object on an inclined plane with no friction, would the acceleration be less than, equal to, or greater than the normal acceleration due to free fall? Okay, so the answer to the question is definitely less than 9.81 meters per second squared. Okay, so an object on an inclined plane, if there's no friction, it is going to have acceleration. It is going to accelerate down the plane, but it's going to accelerate with a value less than that of the normal freefall acceleration. And you can think of the limiting case. One way to approach a lot of physics problems as you're thinking situations through is to look at what's called the limiting case. Okay, so what I mean is, so imagine we have an inclined plane, and imagine we're thinking, okay, what happens to the acceleration in the limiting case? So if theta went to, let's say, 0 degrees, what would happen to the acceleration? Well, clearly if theta was 0, the inclined plane would be flat. You just have an object sitting on the ground. There wouldn't be any acceleration at all, okay, because it would just be sitting on the ground. Now, the other limiting case would be, okay, so what would happen if the angle went to, let's say, 90 degrees? Okay, so let's say you made the inclined plane steeper and steeper and steeper, and you got the angle up to 90 degrees. Right, well, what would happen to the acceleration? I mean, in that case, basically you're talking about a wall. It's not even a ramp anymore. If it's straight up and down, it's basically a wall. The object would just fall off the wall and be in free fall. And guess what the acceleration would be then? It would be about 9.81 meters per second squared. And so clearly, then, if you think in terms of the limiting case, as long as the angle is somewhere between 0 and 90 degrees, the acceleration would have to be between 0 and 9.81 meters per second squared. Okay, and so that means, generally speaking, the acceleration would be less than 9.81 meters per second squared, which is why the answer was the first option. Excuse me. So an object sliding along an inclined plane with no friction, obviously it would be different with friction. Well, it'd still be reduced with friction, I guess. but it would have an acceleration less than the acceleration due to gravity. Okay, so let's talk more about solving problems with inclined planes. Okay, so let's say we have a box on an inclined plane, and let's say this box is sitting at rest. Okay, what I want to do first is I want to draw the FBD for this box. Okay, so the box is at rest. Excuse me. The box is at rest. I know that the force of gravity on the box is going straight down because gravity goes down. The normal force on the box, remember the normal force always acts perpendicular to the surface. The word normal is a math term meaning perpendicular. And so the normal force is not going to act straight up, but it's going to act at an angle so that it makes a 90-degree angle with the incline, something like this. Okay, so the angle between the plane itself and the normal force would be 90 degrees, by definition. Okay, normal force is perpendicular to the surface. Now, if the box is at rest, clearly if there is no friction, the box would want to slide down the incline. So the fact that the box is at rest means there has to be something keeping it from sliding down. And that force would be static friction. Okay, and static friction would be going up the incline, because if it's trying to slide down the incline, friction acts in the opposite direction. Okay, so we have Fn, FFS, and we have Fg. And so let's say we want to, approach this problem. We write Newton's second law. F net x equals max. F net y equals may. And let's just talk about what the forces would be on this object. Now, obviously, if it's at rest, both the right side of both of these equations would be 0. But let's think about the sum of the forces. In the x direction, we would have, static friction, but static friction is not acting in the x direction because it's at an angle, because it's going up the ramp. And so we would have the x component of static friction plus, let's see, what other x forces do we have? Gravity is going straight down, but the normal force is also at an angle. Okay, and so we would have an x component for the normal force. Okay, so we would have F and x. And then in the y direction, we would have, let's see, there would be a y component of normal force. There would be a y component of static friction, so we would have FFSY plus the force of gravity. Now, I don't know about you, but that's a lot of components going on. Okay, and so you could set the problem up this way, but it would be kind of a pain, and it would be way worse if the object is moving, because if the object, let's say, was sliding down the plane, then it would be accelerating in both the x direction and the y direction. Okay, and so both of those things would be happening at the same time. Okay, so that's kind of a pain to deal with. And so in order to solve inclined plane problems, there is a much easier approach. Okay, so here is how you handle inclined plane problems. What we're going to do is we are going to change our coordinate system. We are going to specifically rotate our coordinate system. Okay, so if you think of the normal coordinate system, what that would look like is you have the positive y direction going up and the positive x direction going to the right. Okay, that's like a normal coordinate system that we would be used to. Okay, I'm just going to erase the FBD so there's more space. What we're going to do is we're going to rotate the coordinate system, and we're going to rotate it something like this. We're going to rotate it so that the y direction is now perpendicular to the incline, and the x direction is now parallel to the incline. And I can probably do a better job drawing it if I draw it like on the incline. So our new y direction would be that way, and our new x direction would be that way. All I'm doing is I'm taking the same coordinate system and I'm just rotating. And there's a reason I'm doing that. Okay. This is a 90-degree angle, by the way. It's hard to tell because my bad drawing, so I apologize. But we're rotating our coordinate system through some angle theta. Okay. And so theta plays in right here because theta is the angle that we rotate the coordinate system through. Here's why we want to do that. If we now go back and think of the sum of the forces, okay, we still have the same three forces acting on the box. We haven't changed any of the three forces, we've just rotated the coordinate system. But by shifting the forces, when I go to write down the sum of the forces, guess what happens? Okay, I think of the x forces. My new x direction is now parallel to the incline. Okay, which forces are acting parallel to the incline? Well, the force of static friction, in this case, was going straight up the incline. That's in the x direction. Okay, I don't have to worry about any components for the force of static friction. That is acting in the positive x direction. All right, now the force of gravity, which is going straight down, remember we've rotated the coordinate system. This now has a component in the x direction. And I'm going to try to draw this even though I'm not really good at this. Okay, but because we are rotating our coordinate system, this angle is theta. This is FG going straight down. There is a component of FG going down the incline parallel to the plane, and that I call FGX. And so that would be my other x force. Okay. In the y direction, when I do the sum of the forces, I have Fn. Okay, not Fny, because remember, we rotated the coordinate system, so now my new y direction is perpendicular to the incline. And that's perfect because that's the exact same direction that Fn is going in. Okay, and so Fn is automatically going in my new y direction. I don't have to worry about components of Fn. Okay, likewise, FFS is parallel to the incline. That doesn't play a role at all in F net y. And so now I only have two forces in the y direction. I have the normal force, which all of it is going in the y direction. And I also have a component of gravity, which I will draw right here. And that would be FGY. Okay, that is my only force in the y direction. Now, it's a little bit weird because now we have x and y components of gravity, whereas before gravity always went straight down. And it seems like, we've made things more complicated, but we've actually simplified things. Because remember, in the normal coordinate system, we would have x and y components for Fn and FFS. Here, we still have to, deal with components, but we only have to deal with them for one force and not for two. Plus, there's an extra benefit. An object on an inclined plane will never, ever, ever, ever move in the y direction. Because think about this box sitting on the ramp. If it were to move in the y direction, either it would have to go, bury itself into the ground, which is not going to happen, or it would have to fly up off of the inclined plane into the air, and that's also not going to happen. So for inclined plane problems, F net y is always going to be equal to 0, no matter what, because the object cannot move in the y direction. Okay, that means if it's accelerating, it can only accelerate in the x direction because of our rotated coordinate system. So that's the other benefit of using a rotated coordinate system. Okay, so pause it there. Make sure you get that down in your notes. The last thing I want to add, though, before we start doing some examples, is how do you calculate FGX and FGY? Well, based off of this picture I drew, we can see, it's kind of hard to see actually. I don't know what I just did. We can see that from my poor drawing that this is a triangle. This theta is the same angle as the incline, and so the x component is the side of this triangle opposite to this angle. So in other words, the way to calculate FGX would be by doing FGX would be equal to FG, which in this case would be the hypotenuse, times sine theta. And likewise, FGY would always be FG cosine theta. Now keep in mind you would only be using these equations if you were doing an inclined plane problem with a rotated coordinate system. Sine theta and cosine theta can only have a value between -1 and 1. And so before, when we talked about how an object on an incline is always going to have a reduced acceleration compared to free fall, so you can see that in the FGX equation because sine theta is always going to be less than 1. Okay, and so you're always multiplying a number less than 1 by the normal free fall force of gravity, Fg. Okay, so pause there. Make sure you add both of these equations to your notes because you need them to be able to do all of the inclined plane problems. Alright, so let's do some examples. Okay, I don't think there's anything new here. I think I already talked about all of this. The equations are down here. I'm going to link a video if you want to watch about 5 minutes of the video. You can maybe get a better understanding of where these equations come from since my picture kind of sucks. Okay, so I would encourage you to check out at least between 233 and 731 of this video, and that might help you. Okay, so let's do some problems. Okay, same steps that we've done before in second law problems other than the rotated coordinate system. Okay, you start with an FBD, you determine if the object is accelerating or not. It will never be accelerating in the y direction on an inclined plane problem, so that's a freebie. And then, you write down the sum of the forces. Okay, so let's start with the easiest example I can think of, example 1. Okay, example 1 says a box of mass 8.3 kilograms is placed on a frictionless inclined plane that makes an angle of 35 degrees with the horizontal. Alright, so I'm going to draw my inclined plane. There's an angle of 35 degrees. Boop. I have the box on the plane. Boop. And I know the mass. Okay, I'm asked what is the acceleration of the box down the plane. Now, if I'm using a coordinate system that looks like this, that means up the incline is the positive x direction. In that case, this box would have a negative acceleration because it's obviously accelerating down the incline. By the way, please ignore the fact that this is poorly drawn. Actually, let me just redraw this. I don't want you to get the wrong idea just because I can't draw a straight line. Okay, so this is 35 degrees. Here's the box like that. Okay, so the FBD would look like FG going down, normal force perpendicular to the surface, and that's it. Okay, I mean, it says that there's frictionless. It doesn't say anything about applied force. Those are the only two forces acting. Okay, so we have the FBD. Like any second law problem, we go to our second law equations. We determine is the object accelerating. So I have F net x, F net y. I know because it's an inclined plane problem that this side is automatically 0 because there's no way it's moving in the y direction. And in the x direction, I say, is it accelerating? And the answer is probably yes, because it's asking me to find the acceleration. So I'm looking for ax, because ay is 0. And then I write down the sum of the forces. What forces are acting in the x direction? Because of my rotated coordinate system, I have FGX. FGX. In the y direction, I have the normal force, and I have FGY. Okay, so my setup is done. Now I can start doing calculations. Remember, FGX is FG sine theta. And FG is itself mg sine theta. And so I can plug in for FGX, I'll do that up here, I can plug in 8.3 times negative 10, because that's little g, that's the acceleration due to gravity, times sine of 35 degrees, and that's equal to 8.3 ax. Notice, by the way, normally we would just divide both sides by 8.3, but if we divide both sides by 8.3, this 8.3 cancels, and this one also cancels. And so you get an interesting fact. The acceleration down the incline actually does not depend on the mass of the object. Okay, so ax is basically just negative 10 times sine 35. And if you do that, you get negative 9.7 meters per second squared, and I am done. Okay, so that is the acceleration of the box down the plane. Remember earlier at the beginning of this video, I asked you, if it's less than, equal to, or greater than 9.81 meters per second squared. Here you can clearly see 5.7 is less than 9.81 meters per second squared. Okay, so that is example 1. That's the most basic inclined plane problem you could have, because there's no applied force, there's no friction. Okay, so pause there if you need to look at that some more. Okay, example 2. It says a box with a mass of 250 kilograms is pushed up a frictionless inclined plane which has an angle of 30 degrees. The box is pushed with an applied force of 3,000 newtons. Okay, so we still have an inclined plane problem. There's no friction, but there is an applied force now. So this is 30 degrees. Here's my box. The FBD would look like this. Force of gravity going down, normal force going up, and then it says there's an applied force up the inclined plane. Now, up doesn't literally mean up. Everybody knows if I tell you to push something up the hill, you're not literally going to push straight up, but you're going to push like this way. Okay, so the applied force is at an angle, but in my rotated coordinate system, it's actually pushing in the positive x direction. Okay, so I have my FBD. Before I even look at the questions, I'm just going to do my setup. F net x equals max is accelerating in the x direction. I don't know, probably, so I'm just going to leave that in there. Although I do know for a fact that it's not accelerating in the y direction. We've talked about that before. Okay, so may, this is equal to 0. I write down the sum of the forces. So now I have to think what force is acting in the x direction. Well, FA is completely in the x direction in my rotated coordinate system. Plus I have FGX. And in the y direction I have FN and FGY. Alright, so now I look at the question. The question says calculate the acceleration of the box. Well, I have FA. It's given to me in the problem. It's 3,000. FGX I can find very easily, because that would just be 250 times negative 10 times sine of 30 degrees. Remember, FGX is FG sine theta, and so that would just be negative 1,250 newtons. Alright, so I have FA, I have FGX. This is now an easy problem. 3,000 plus negative 1,250 equals 250 AX. 3,000 minus 1,250 is 1,750. And so AX is going to be 7 meters per second squared. Okay, so it would accelerate up the plane at 7 meters per second squared. Easy problem. Now, the second question says, calculate the acceleration that the box would have if the applied force was simply removed. So all that would change is FA would go away. And so if FA went to 0, all I would have is FGX. That means my equation would become, this equation right here, would become negative 1,250 equals 250 AX. If you divide both sides by 250, then now you get A equals, let's see, that would be negative 5 meters per second squared. Okay, and so if you stop pushing all of a sudden, it's going to accelerate down the incline pretty quickly. And that's it for example 2. Pause there if you need to look at it. Okay, so we're going to do one more example with friction. And then that'll be it for inclined planes. And hopefully you appreciate, aside from the novelty of the rotated coordinate system, these problems are really not anything that you can't handle. Okay, so now we have a problem, let's say crate, blah, 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 ramp, blah, blah, blah. Now we have friction because it says it's a rough ramp. Okay, still has a 30-degree angle. We're given the coefficient of kinetic friction. Okay, so here's mu k. Wow, I misspelled k somehow. Mu k. Alright, so the FBD, we have force of gravity going down, normal force perpendicular to the incline, and let's see, it says it's sliding down a ramp, which means that friction would act up the ramp, because it opposes motion, so this would be FFK. I go to my second law equations, F net x equals max, F net y equals may. I say, is it accelerating in the x direction? Yeah, probably. It's asked me to find the acceleration, so probably. So that would be 128x. This side is always going to be 0 for an inclined plane. We talked about that before. Write down the sum of the forces. In the x direction, all I have is actually I have got two forces. I have FFK plus FGX. Now, FGX I can find really easily because that's just mg sine theta. FFK, though, remember the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. Okay, so how do you find the normal force? Well, in the y direction, when I do the sum of the forces, I have Fn plus Fgy, and they both add to be 0. Okay, so I can find Fgy, use that to find the normal force, use that to find FFK, and then I'm basically done. Okay, so let's see, what is FGY? FGY is Fg cosine theta. So that would be 120 times negative 10 times cosine of 30 degrees. That one I need my calculator for. Okay, so 1200 times cosine 30. Okay, so that would be negative 1039.2 newtons. Okay, so Fn plus negative 1039.2 equals 0. And so Fn is equal to 1039.2 newtons. Now I can find FFK because FFK is mu k, which is 0.4, times Fn. And so I just need to multiply that by 0.4, and I get, I don't know, let's call it 416 newtons. Okay, that's the magnitude of the force of kinetic friction. Based off of how I drew this, that is acting in the positive x direction. And so when I go to plug in, I have FFK now. FGX I can calculate because FGX is Fg sine theta. And so that would be 1200, or 120 times negative 10 times sine 30 degrees. And that would be, if you calculate that, you get negative 600 newtons. Okay, so now I'm basically done. I plug in FFK, I plug in FGX, and I will do it right here because I'm running out of space. FFK was 416. FGX was negative 600 newtons. Okay, it says plus FGX, but FGX is negative. That's why I just put a minus sign there. And that's equal to 120 AX. And then it's just a little bit of algebra from there. Okay, 416 minus 600 divided by 1200, and you get negative 0.15 meters per second squared. Okay, and so that would be the acceleration of the incline, or the acceleration of the crate on the ramp. Okay, so it's still accelerating down the incline, but not very much because there's so much friction. Okay, so pause it there if you need to look at that some more. And then on your own, I want you to try to answer the last question on your own. It says, determine what force would need to be applied along the incline to stop the crate from sliding at all. Okay, and so if you understand conceptually everything that's happening, this should be a very, very easy question. You shouldn't have to do a ton of crazy calculations to answer that second question, but try to do that one on your own. Okay, so that is how you do inclined plane problems. The next quiz you have will be over inclined planes. They're not complicated or anything as long as you understand how to do the rotate coordinate system. They're just like any other second law problem. As always, please let me know if you have any questions, and I'll see you guys in the next video.